Gunther, did you receive my email?
Yes, thank you very much.
Okay.
Had no time to answer it.
To start.
So, hello, Hubert.
Hello, Günther.
Yeah. Well,
so it's
hello,
about
everybody, and welcome to this course on Near-rings. I'm Gerhard Betsch. You will have seen this on the on your screen. Hopefully, you will have a good reception on your PC. It's my impression that you can understand everything. Last winter, Günter Pilz wrote the formulas on a blackboard, which he had in his study. I do not have a blackboard or a wooden white or a modern whiteboard, and my study is far too small to establish a whiteboard. Hence, we have to change the method. During my professional life, I taught a lot, but always in front of a blackboard, writing on this blackboard. Hence, I have practically no experience in lecturing by Zoom. Anyway, I try to make my talk more accessible by presenting the writing on blackboard in a different form. And Günter Pilz is kind enough to present the pertinent pages. I plan to present selected topics, starting with basics for the benefit of newcomers. I do not know most of you personally, so I do not know your level of information on Near-rings, so I better inform on some basics. Then I try to continue a few topics which Günter Pilz presented at the end of the winter term. Some repetitions in varied form, some variations. Then I plan to go on to present more on planar near-rings. Here. Planar near-rings, in particular, some topics on circularity. And then the main bulk of this course will be on structure theorems and, well, describing simple and semi-simple near-rings in a suitable sense. And then I have in mind to present a few things on axiomatic radical theory for near-rings. There is a very developed axiomatic radical theory for rings, and this can also be done for near-rings, which provides rather astonishing deviations from the ring case, and that's the really interesting thing. All right, so let's start. I hope you you have a good you can receive everything very good. And if you feel that, well, if something is wrong, of course, I need your protest. And if you want to be discussed certain things in greater detail, please say so. But, well, now let's start. Please, page 1. Good? Yeah, very good. Yeah, okay, very good. A near-ring is a structure where N is a group. Commutativity is not requested. Multiplicatively, it's a semigroup. This means the multiplication is associative. And different from Günther, I assume, for my purposes, the distributive law A times B plus C is equal to AB plus AC. In Günther, suppose the opposite distributive law. Maybe I will say a few things for this as a motivation. Well, if we assume a structure of this kind, we have some simple consequences. AB is AB plus 0. We get that A times 0, which is the neutral element of the additive group, is always 0. I assume in addition 0 times n to be 0 for all n. This near-ring of this type is usually called zero-symmetric. In suitable places, it will be discussed what modifications are necessary if a general, not necessarily zero-symmetric near-ring is discussed. I have the feeling that the music plays in zero-symmetric near-rings, and so it's meaningful to concentrate on these structures. Well, there is a lot of obvious definitions: subnearing, homomorphism, automorphism, and so on. Could you please move up a bit? Fine, yeah. We take from group theory, subgroup, normal subgroup, homomorphism, isomorphism theorems. That's clear. And the concepts of permutation and permutation group on a set. The elements, they induce a mapping of a set X into itself. And the image of X under G might be called in different ways, and we shall use various ways for good reason. Kind of a generalization is the concept of action of a group. My supervisor, Wieland, was a specialist on permutation groups, and so he thought in the concepts of permutation groups. Action of a group on a set, this means that G induces certain permutations on the set X. We have it to each small g in capital G, there is a permutation of assigned a permutation of X, and and this G acts on X like theta G of X, and there's has the obvious consequences. If I take an element y in X, then G of X, capital G of X, will be the set of images of X under all elements of G. This is the orbit of X under G. And, if you introduce a relationship Gx equals Gy, this means they both are X is in the orbit of Y and Y is in the orbit of X. Dealing with permutations means we have to consider the stabilizer. That's the subgroup of G in G acting on X, such that Gx is X. And we will focus on groups with special conditions on stabilizers. We have a simple equation that the length of a stabilizer is, the length of an orbit is the index of the stabilizer of any element in this orbit. This is one of the most useful equations in elementary group theory. For instance, fine proof of Sylow's theorem results heavily on this equation. Now, we have to have left and right ideals. I like to define this. I assume a normal subgroup of the additive group of N, and the left ideal means that a congruence modulo L is left stable. You might multiply it from the left with any element from N. And the right ideal, you have the same from the right. And this may be modified. You may assume that for any R in R and for any S in N and N in N, R plus S times N minus Sn is in R for all R in capital R and Sn in capital N. On the other hand, or another characterization of right ideals, a right ideal is a kernel of an N homomorphism of the additive group, considered as an N group, but this will be defined later in the chapter or in the in the chapter of structure theory. And a right and left ideal is an ideal, and this is may also be characterized as a kernel of a near-ring homomorphism. Some very preliminary and incomplete hints to literature. There are several books by Günter Pilz. James Ray Clay wrote a very thorough monograph, Near-rings, Genesis and Applications. And in the next year, 1993, he wrote a book on the equation AX is equal to BX plus C. This is the interesting equation in the context of near-rings, and in particular in the context of planar near-rings and its special cases. Let me come back. I want to discuss in this series some leftovers from the winter term, which might be, we might go into greater detail. Then I will speak on near fields and sharply two transitive permutation groups. Finite near fields and finite sharply two transitive permutation groups are almost the same that was mentioned in passing at the end of the winter course, and I think it's worth looking, taking a more detailed look into it. Then I will mention at least near domains. That's a structure which was interested by Katzel and his school. Then this involves the structure and construction of planar near-rings and their applications to BIBD designs. And the main chapter will be structure theorems of near-rings. And well, I hope to discuss a few steps towards a general radical theory of near-rings. Now, page 3. Let me begin with a closer look at highly transitive permutation groups. It's in discussing the structure theory, we have to discuss the case when is a near-ring acting on a group, the near-ring of all group mappings of itself. And in a similar way, in a similar type of spirit, the permutation group theorists in the 19th degree, they were interested in highly transitive permutation groups. And they were looking for theorems either, if we have a high degree of transitivity, then it must be the symmetric group or the alternating group, or do we have further groups? If we have K, if we have six transitivity, we have just the symmetric group and the alternating group of on 8 digits. The alternating group on K digits is K minus 2 transitive, and therefore this is the reason for this difference. In case of K5, we have the symmetric, the alternating, and now you will see in 5, 4, 3, 3 of the Mathieu groups. They were discovered in the late 19th century by a French mathematician, Mathieu. M23 is a stabilizer of an element in the set on which M24 is acting, in the same way we come from M23 to 22, which from 5 to 4 and to 3, that's a reduction of transitivity. These, we have no assumptions on finite or infinite. They come out. These finite groups. In the infinite case, in the infinite case, an important example of three-dimensional, of free transitivity are the Möbius transforms, which you know from elementary courses on complex analysis. You may see what the one-point compactification of C consider as the projective plane over C, over the complex numbers. And these are in a slightly different form, the projective transformations of this line. And they are sharply free transitive. you will remember if you did a course on complex analysis, then you can fully determine such a Möbius transformation by prescribing the mappings of 3 points. In this case, to exclude trivial mappings, we assume that the determinant is not equal to 0. When I come back to K5 up to 3, there is an old theorem due to Camille Jordan, which says that sharply. So far we were discussing multiple transitivity. Now we discuss sharply multiple transitivity. A sharply car-transitive finite group, or sharply for instance, a car-transitive group maps not only a k-tuple of different elements into any given k-tuple of distinct elements, but it has the additional property that this element which induces the permutation, which is the permutation, is unique. There's only exactly one element in a sharply 5-transitive finite permutation group there, or group acting on a set. There's exactly one element moving a given quintuple into another one, into another quintuple of different elements. And here again, in the case of sharply, we have smaller Mathieu groups. For k and 3 and 2, k equals 3 and k equals 2 in the finite case, I refer to the following pages. Just when did Mathieu live? He was from Betsch in the Lorraine. And he lived, Mathieu introduced his groups simply as permutation groups, and the description was rather difficult, so difficult that Abraham Miller wrote a paper in which he proved that M24 doesn't exist. He had to do penitence. The next year he wrote a paper in which he admitted that M24 exists and did some work on a representation. To represent the Steiner system, to represent the Mathieu groups, the suitable systems are the Steiner systems, named after Jakob Steiner, Swiss mathematician. STKN is a block design. It means a set of points which are, at least some of them are combined in a block. And there are n points, and the blocks are with k elements. And every T subset of points is contained in exactly one block. And here we can say that M24 is the automorphism group of a certain Steiner system, which Ernst Witt investigated carefully. Therefore it's called Witt design. Here we should have, I made a mistake. Here we should have M12. It's false, not the 23. All right. So in passing, please, page 4. Page 4, please. Yeah. It was mentioned in passing that a finite near field and the finite two-transitive group, permutation group, of course, is actually the same. Now this, I felt that we should look a bit more closely on this connection. And let me be given a phi, the sharply two-transitive group on a set X. We know from group theory, or we could know, if we don't know, let's check the books. In this case, remember, we have finite sharply two-transitivity, and we have a finite near field. Then we will build up a finite near field. Then the set must be of p to the n elements, so that the degree of this permutation group is of degree p to the n, and the order of this p is p to the n times p to the n minus 1. This is relatively easy to prove, but well, I take this from group theory. Furthermore, there is a normal subgroup of phi, abelian, which consists of those elements without fixed point and together with the identity. Now, to be consequent, this should be a Greek eta, and this should be a Greek mu, but that's pedantic. Let me M be the stabilizer in phi of an element 0, and let the Zx be given in the form 0, 1, A, B, and so on. It's absolutely, we are absolutely free to decide which elements we call 0 and 1. It means that these elements will be 0 and 1 in the near field to be constructed. Then, because we have sharp transitivity, there is exactly one eta A in H, which moves 0 to A, and exactly one mu A in M, which moves 1 to A. And now I'm in the position to define A plus B, that's eta B of A, and A times B is mu A times B. If A is not 0, if A is 0, I define A times 0 equals 0 times A is 0. And we have then the proposition that this X of p to the n elements with this addition and this multiplication is a near field. It's could be there is a, there should be an A here. All right. That's the picture is not complete. It's on the border. There should be an A. That's obvious, and this addition is invertible and associative. And furthermore, we have now page. Yeah, I see. I could remove your pictures. well, page 5, please. Would you please, Günther?
It should be there already.
I don't see it. I have it very small.
It should be there, Gerhard. Page 5.
Page 5. It's on the right side on my screen.
I didn't change anything.
Could you maybe return to? Well, it's the key. Very good. Hello.
Okay, Gerhard, it should be there already for some time.
Right. Here we have it. Yeah, we have eta B A. A is eta A0, so we have this eta B, eta A0. And we have commutativity, that's from group theory. I mentioned this, eta A, eta B. And so we have eta B0 is B, so we have eta A, eta B. Eta BA is eta AB, so we have commutativity in H. And well, this is associativity and so on. This simple. Distributivity might be worthwhile. We have this equation A times B plus C is mu A, B plus C is mu A, eta C, eta B0, and so on. And we end up with AB plus AC. And this completes the proof. It would be stupid to discuss the trivial parts. Hence, I may say classifying finite sharply two-transitive permutation groups is equivalent to determining all finite near fields up to isomorphism. This was achieved by Hans Zassenhaus in 1935-36, Hamburger Abhandlungen 11. And he came up with the result: all finite near fields are Dixon near fields with 7 exceptions. So we have to look back to the construction of Leonard Eugene Dixon of 1905. He starts with a Galois field and he distorts the multiplication. This this is one possible way to do this is if you if you look at F star, these are the non-zero elements of the Galois field, and this contains exactly one normal subgroup Q1 of index 2. Index 2 means normal subgroup in any case. And then I define multiplication in the addition is untouched. remains as it is. Then we get this, we take, if A is in Q1, that's, yeah, you may say that's the subgroup of squares. We take the old multiplication and we distort by an element phi. If A is not a square, that's that's a phi automorphism, and well, that's here you are free to take certain choices. And for the exceptions, I thought maybe I should write them down, but that's would be a simple report. See the literature. Dixon's paper, or two papers of 1905, belong to the concept of axiomatic. His example of a proper near field on Galois field with 9 elements showed that one, if you have all the axioms of a division ring, and one, but only one distributive law, you cannot prove the second one. And Veblen and Wedderburn, who belong to the group around Moore in Chicago, they used this near field in 1907 to give an example of a non-Desarguesian and non-Pascalian projective plane. If it's not Desarguesian, it's automatically not Papian or Pascalian, as people said in those days. But the pertinent theorem by the pertinent theorem that that Pascalian or Papian implies Desarguesian was not approved yet. So one had a significant gain in the field of geometry, non-Desarguesian geometry. What does this mean? There's a classification of Hahn-Fried Lenz and Professor Barlotti in Bologna of projective or affine planes. If you take off one line from a projective plane, you have an affine one. Lenz worked had his paper in 1954, Barlotti in 1957. If you have no special assumptions, you may construct a coordinate domain, which is normally called a ternary field. If you have a near field, we are showing that in the case of planar near field, the being zero symmetric follows from the other axioms, and we were shown in the proof that any finite planar near field, any finite near field is planar. So we have, if we have a, oh well, that should be the. I'm sorry. This should be here and this should be here. If we have a planar near field as coordinate domain, then the projective plane is of a type 4A in a long list of projective planes from the fully the finest planes over the reals or over where the pappus axiom is is fulfilled. If you omit commutativity of multiplication, you still have but the division ring, you still have it as Argesian. And if you are, sorry, planar near field here, if you have a planar near field, then you have a type which is fully described in the papers by Lenz Ballotti and has a certain number. This list is a very, very instructive, and people worked for a long time on these things. Well, could you go to 6, please?
This was 6.
That was 6. Ah, yeah. Well, now I, as a repetition, I give the definition of planarity again. Let any be a near-ring, then we nearing with the distributive law, which I assumed. Then we call, we define that's a congruence relation. If A is in this way congruent to B, if for all n a n equals to Bn, and it is planar if for A not congruent to B, this equation, remember, it was the title of a book by Clay, AX equals BX plus C has a unique solution. But to avoid two trivial cases, we assume that we have at least 3 different classes modulo this congruence. And in a planar nearing, or well, this the definition would be, or in a planar nearing, well, we define normally, or we denote by A all elements which are congruent to 0. These are all elements such that A times n is consists of the 0 alone. Could you move a bit up? And I will now show how to construct a planar nearing from a Ferrero pair to honor Professor Giovanni Ferrero in Italy from additive group N and Phi being a fixed point free abbreviation FPF group of automorphisms, and of course not only the identity. If you're not acquainted with this concept, fixed point free means if phi of n is n, then this implies either n is the neutral element of n, or phi is the neutral element of the group phi. And in the infinite case, we have to have this condition minus phi plus 1n is surjective. Otherwise, it's clear in the infinite case, we have to be careful in the finite case, if we have an injection between sets of the same cardinality, this is automatically a bijection, and in the infinite case, we have difficulties in this respect. Now we divide n into orbits under phi. 0 is an orbit of itself, and the rest is divided into equipotent blocks of the same length. This is a partition of n-0 into orbits of phi on n, and for all bi is the length given by the order of phi, and in the finite case we have in the infinite case you would have to have some equivalence of cardinality, and in the finite case you have order of phi divides order of n-1. Now we can choose at random, at complete liberty, what we do, choose representatives EI of each BI. We are free to define 0 multiplication on certain orbits, but it would be advisable to include all orbits into the domain where we have non-zero multiplication. BI is the orbit of EI, and A is 0 and the union of orbits. And now if A is in A, what we have defined to be the domain of 0 multiplication, we must consequently define AX as 0, and in particular 0 times X is 0, 0 symmetry, and N star, these are the orbits which we want to include in a non-trivial multiplication. If we consider EI, then if we consider A in BI, then we have exactly one element, phi A of EI is A. And this is, and then we define A times X is phi A of X. And I should mention X and phi AX is in the same orbit, because phi A is an element of phi, and this doesn't move outside of the orbit. So we have for EI, from BI, EI is idempotent, and this orbit is may also be represented in this way, N to N star EI. Now we have to show that this N plus with this multiplication is planar. If we are interested in block designs mainly, we have already sufficient information to build a block design. Let me explain this from the example from the winter term, which Günther discussed in detail. We start from the additive group of the Galois field on 7 elements, that then given by the smallest positive residue modulo 7. N star, the non-zero elements, form a cyclic group which of order 6, which has a cyclic group of order 3 consisting of 1, 2, and 4. And by multiplication, it doesn't matter on which side, this phi induces fixed point 3, two fixed point 3 automorphisms, and of course the identity automorphism on N. And the orbits, the orbit of 1 is 1, 2, 4, and the orbit of 8, the orbit of 3 is 3, 6, 5. And page 9, please. I repeated this. This list. We have a total of, yeah. It's clear from the theory, which I will discuss next time, that you get all the blocks from these two orbits by adding adding the non-zero elements of N, and this makes it almost a mechanical thing to write down this list. Here in all those columns, you have 1, 2, 3, 4, 5, 6, 0. That's 7. 2, 3, 4, 5, 6, 0, 1, and 4, 5, and so on. And the same here. And you get 14 blocks. F is 7. The number of blocks is 14. Each block has K equals 3 elements. The number of blocks in which a particular element appears is 6. The number of blocks containing a 2 set of points, for example, 0, 0, and 1 is 2. And we have these equations. I think it's important that we cannot only give an interpretation of this of the system of blocks. For instance, the points were certain elements, and the blocks represented a certain experiment with these 3 elements. We can let's see. It's similar to duality in projective planes. We can also start with a blocks. If we are given this if we are given these points in these blocks, we can now focus on the blocks. For instance, you have 14 fertilizers, each one to be applied on 3 out of 7 fields. And then the elements of the blocks are, so to say, the numbers of the fields on which B1 is to be applied on field number 1, 2, and 4. B2 is to be applied on field number 2, 3, 5. And I'll show you next time. This gives a quite nice list with symmetries, and we will see this next. We will see this in a week. statisticians usually test the efficiency of a block design by this quotient, RV, divided by RK. In our case, it's 0.77. It's 7/9, 7 divided by 9. This is not bad, but there are even better. There are even better block designs, and yeah, this will be be discussed next time. As I pointed out, I had no idea what I should, how much of the stuff I should prepare for projection, and the following is not ready for projection. So I think we have to end our session for today, and I'll do my best next time. So see you in a week.
Okay, thank you very much, Gerhard. There's no need to extend this to the full length of time. You have done all the sheets you sent me, and I think it's a good point to stop here as well. In the name of all of participants, I really thank you for giving this lecture, and I'm looking forward to seeing you next week again.
Oh, you're welcome.
So goodbye to
yeah, goodbye.
And thank you very much for coming.
Thank you. Thank you.